Alright friends, welcome back. In this video I'd like to go ahead and continue Chapter 3 by taking a look at Section 3.2 of your textbook, and what we're going to do is switch gears from quadratics like we did in the last video and start to talk about the wider world of all polynomials here in this video. And so what we want to do here is, of course, talk about the graphs of polynomials, and later on we're going to kind of work up in the video to actually learning how to sketch the graph of a polynomial. And so let's learn some things about the graphs of polynomials first. So first and foremost, one of the most important things about the graph of a polynomial is that these graphs are always going to be continuous, okay? And so what continuous, of course, means is that you could draw the complete shape of the graph without lifting up your pencil, okay? You could just draw the complete shape with one smooth stroke of the pencil. All right. The other thing about polynomial functions is that when you graph them, there are no breaks. So again, that's part of it being continuous. But then the other thing here is that there are no sharp turns in a polynomial's graph, okay? So you may remember the graph of something like f of x is equal to the absolute value of x. If you were to actually graph that, then remember that has your characteristic v shape. That has a sharp corner there at the vertex of the absolute value graph. That's not going to be a thing on a polynomial. You should find that you only have nice smooth curves on a polynomial shape, so no sharp turns here. So if we take a look at a couple of examples and just ask ourselves if these are the graphs of polynomial functions, I would say here that on this first one, that is going to be a no, because we do have a break in the graph. We would have to lift our pencil to bridge the gap from one piece to the other piece there. This other one is good to go. That is one continuous curve with no sharp corners. Here I'd have to say, unfortunately, no, that is not the graph of a polynomial because of this sharp corner right here. Polynomial functions never have those. And then if you take a look at this last one, I dare say that is going to work out here for us. It's nice and continuous. It has some smooth turns as you go throughout the shape. That is a pretty classic polynomial function graph there. Okay, so taking a look at the function formulas for polynomials here for a minute, you'll notice that they have a familiar pattern, and that pattern just keeps going as you take a look at polynomials of higher and higher degree here. So we do give them names according to what their degree is. So in the case where your degree is actually 0, which keep in mind in this case here, this is a 0, that is a constant, just some number. But typically we also characterize this as being times x to the 0 power, which remember that anything to the 0 power is simply just going to be the number 1, okay? So that's why we end up with that constant function there. But as you go through your linear functions, remember that is typically something that was taught to you as mx plus b, but we have the same general shape going on here of your function formula, which is playing the role of m as your a1, playing the role of b as your a0, that kind of thing. Your quadratics that we talked about in the last video, of course, are represented here, degree 2 polynomials. Your cubics after that, degree 3, quartics are degree 4, you have your quintics, degree 5, and then et cetera, et cetera. But in the general case, where we just have a degree n, that is something that we might go ahead and write out like this. That's not something we really give a name to. But what I want us to do is go ahead and take a look at how many bumps there would be on the graph. And by bumps, what I mean are, of course, turning points, right? So, of course, if you were to go ahead and create some quick sketches of these, any sort of constant function, if you were to go ahead and graph that, would just go ahead and look like a horizontal line for you. There's no turning points there on a flat horizontal line. For a linear function, we say that it has 0 turning points there as well, because these could be your diagonal lines, but it's the same thing. There's no real turning points that you would have on the graph there. For your quadratics, if we were to draw a quick sketch of that, remember these are your parabolas from the previous video, and we would have one turning point that we go from increasing to decreasing, or vice versa. And so we would say that we have one point there that we have as a turning point. For your cubics, a lot of these look like you turn once and then you turn again and then go indefinitely in one direction. Of course, that is going to be 2 turning points. For your quartic functions, your degree 4s, those would be ones where I have 1, 2, 3, 4. Again, because it's an even degree, we have n behavior that points in the same direction here, and I would have 1, 2, 3 turning points in that case, and the pattern continues. What I want us to notice here is the relationship between the degree of the polynomial and the number of turning points or bumps on the graph, okay? You'll notice as we go through, it's always just going to be one less, right? If I have a degree 2 polynomial, I'm going to have 1 turning point. If I have a degree 3 polynomial, I have 2 turning points here. So that's going to mean, if in the general case, if I have n as my degree of my polynomial, I'm going to have 1 minus that as the number of turning points that are in my graph of my function, okay? So being able to kind of point that out and keeping that as a tool in our toolbox for being able to make sense out of what the function should look like later, it's going to be pretty important, okay? And speaking of that end behavior, let's go ahead and actually talk about that a little bit more, right? So we have something called the leading coefficient test to determine end behavior, which is kind of a misleading name because it's not the only thing that you look at whenever you take a look at your end behavior. Of course, you want to take a look at your leading coefficient, which is what I have organized here in the table is going down column-wise. This is your leading coefficient that we're taking a look at. But then we also take a look at its degree, okay? So depending on if your leading coefficient is positive or negative, and if your degree is going to be even or odd, that's going to determine what your end behavior is going to look like on your graph here, okay? And so whenever you have an even degree, your endpoints are just going to point in the same exact direction in both cases. It's in the case where your leading coefficient is positive that they both point up. It's in the case where your leading coefficient is negative that they both point down, okay? When your degree is odd, we're going to have some ends that point in different directions. One's going to point up while the other's pointing down, and if your leading coefficient is positive, then overall, as you read throughout the function left to right, you are climbing, 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 climbing. You might also say that as you are increasing over the entire domain. Or in the case that your leading coefficient is negative, then we are falling, 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 falling. Or you might say that we are decreasing as we go throughout that entire domain, okay? And so the way that we would typically characterize that end behavior is just by simply doing a verbal description of what our ends are doing, up, left, up, right, etc., etc. And so that's going to have to also be something that we keep on to as we go ahead and create some sketches of polynomial graphs later, okay? So example 1, let's get some practice with this end behavior stuff, right? So it says determine the end behavior of the following equations using the leading coefficient test. So if we go ahead and do that, remember that we're looking at the degree and the leading coefficient, and I'm just going to talk through these instead of writing them down. You can go ahead and write them down if you like. They're also in the completed set of notes in OneNote as well in the content library. So we are going to go ahead and take a look at each one of these. So the leading coefficient there, of course, is going to be negative. And your degree, of course, is going to be odd there because it's 7, right? So it's the largest exponent that you see. So that is going to mean that we have ends that point in different directions. And because the leading coefficient is negative, then that means that I'm going to be falling as I go throughout that function's shape there. So we'd have a little bit of a shape like that. In the next one here, we have a leading coefficient there that it looks like is going to be a positive 1 for us. So that is a positive number. And the degree, of course, is going to be an even number 4. So because it's even, we have ends that point in the same direction. Because the leading coefficient is positive, those two are going to point upward. So we'd have something that looks like that. All right. In the next example, one of the things that we're going to have to be careful of is that your function is written in standard form before we figure out what the leading coefficient and the degree is. So here, I'm not going to rewrite it. I'm just going to point out here that the leading coefficient would be a positive 1 x to the 5th power, meaning that your degree also here is 5. So we have a positive leading coefficient. We have an odd exponent as our degree here, and so we would go ahead and have two ends that point in different directions and increase as we go throughout the domain. And then finally here in this last example, we have a leading coefficient here that, of course, is negative. We have a negative 1/4, and so because we have an even degree, we would have two ends that point in the same direction, and they would both point down because the leading coefficient there, of course, is negatives here. So I've just went ahead and drawn the pictures here on the homework, and in other locations, like in the textbook, you might see people doing a verbal description of what the end behavior is doing from function to function, okay? And so up to this point, all we've talked about so far are how the number of turning points are related to the degree of your polynomial, and we also talked about end behavior. So it turns out that just equipped with those two facts, you can answer questions like these where you start to link pictures of graphs to the actual function formula. Because again, all you need to look at is the degree and the leading coefficient. So in the case of this first one, we have a leading coefficient that is negative and a degree of 3. That's going to mean that I am going to have some ends that point in a different direction, and it's going to decrease throughout its domain. Something that might look like that. So if you look at your choices down here, really the only ones that apply there are going to be either B and C that match that end behavior. And what we just need to do now is go ahead and calculate that number of turning points that we would expect, right? Since your degree is going to be 3 on this polynomial here in number 1, we would expect 3 minus 1 to be the number of turning points in our function. And of course, 3 minus 1, of course, is 2. So that would mean that I'm not B because that has too many turning points. I would, of course, be C here because that has the turning points that I want, and it also has the end behavior that I want. So I'm going to go ahead and say here that C is the correct answer for that first one. In the case of the next one, I have a positive leading coefficient. It's positive 1. And I have a degree here that is an even number, so I'd have two ends that would both point up, and because the degree is 4, I would have one less than that as the number of turning points, which would be 3, and it looks like the only thing with the end behavior that we're really looking for is going to be part A, and just visually checking here and confirming really quickly, we do have 1, 2, 3 different turning points on that function's graph, and so that checks out. okay? For the next one here, we have a leading coefficient of, it looks like positive 1. And the degree, of course, here is going to be 3, which is an odd number. So that means that we are going to have some end behavior that points in different directions. And we're going to be climbing or increasing throughout the domain. So it looks like the only one with the end behavior, or the ones that we haven't done yet, that's going to be D. And just visually confirming here that the number of turning points should be the degree minus 1. So 3 minus 1 is 2. I have 1, 2 turning points in that function's picture. So that's pretty good. And that, of course, leaves the final one, which is B. We should just visually confirm, right? We have a leading coefficient of -1 and a degree of 5 here. And so that is going to mean, of course, that I'm going to have some endpoints that point in different directions, and I decrease throughout the domain. So that definitely is something that checks out in B. And because I have a degree 5, I should expect 4 turning points. So let's count them up. 1, 2, 3, 4 turning points in that picture shape. So that is going to be a correct answer there. Okay, so again, equipped only with the number of turning points and the end behavior, you can go ahead and answer questions like these where you're matching up the function to its graph. Talk about the real zeros of a polynomial, right? So later on, again, whenever we get to sketching the graph, we need to keep in mind the turning points and the end behavior, but we also need to know where we cross the axes, okay? And so the zeros of a polynomial correspond to x-intercepts on the graph, which will tell us where we cross the x-axis, and so we need to be able to find those. And as a matter of fact, because of all the different interpretations of a function, we get all these different similar but differently named ideas as far as the zeros of a polynomial are concerned, right? So analytically, if you were to solve the equation, you could call them analytically a solution or a zero of the polynomial. Algebraically, if you were to factor the polynomial, you might end up here with what we call a factor of f of x, which would look like x minus the number a, which corresponds, of course, to either the solution or the zero that you ended up with analytically. And then graphically speaking, what these would correspond to, of course, are your x-intercepts. And, of course, these are going to be points with coordinates a and then 0. Okay, so keep in mind that we are going to characterize each one of these using this number a, and because that means that these are a bunch of different languages all for the same idea. Okay, so what that means is if you find zeros, those are going to correspond to x-intercepts on your graph and vice versa, and that's going to really help us out later whenever we create pictures of the sketch of the graph. So here in example 3, it says find all the real zeros of f of x is equal to -2x to the 4th plus 8x squared. You'll notice that I've already gotten us started here by going ahead and completing the factorization here. And the only other thing that we need to do now is go ahead and say, because I'm trying to find the zeros, I'm going to set this equal to 0 and then go ahead and use the zero product property, or the ZPP, to go ahead and figure out what my real zeros are going to be here. So I'm going to end up with 3 different zeros. I'm going to have x is equal to 0 itself, x is equal to -2, and x is equal to +2. I'm just getting these numbers based on that relationship between the 0 being x is equal to a and the corresponding factor being x minus a. Okay, or in other words, I'm just basically changing the sign of whatever you see in the algebraic factor. So you end up with these 3 zeros here, and don't forget that these all correspond to x-intercepts that would have the following coordinates here. So again, that's going to be pretty important whenever we get to sketching these later on. Okay, but that kind of begs the question, you know, like we might go ahead and think about what this graph might look like. I know where I'm crossing. I know that I need to cross at 0 and at -2 and at +2. But it kind of begs the question, you know, like, am I going to be striking straight through the graph at these locations? Or maybe am I going to be bouncing off at these locations? And in what direction, right? Am I going to start above the x-axis, below? We need to kind of figure out what we're doing or how we're touching the x-axis at each one of these locations. And so in order to figure that out, what we would turn to is something called the multiplicity of these zeros. Or in other words, look for repeated zeros in the factorization, okay? And so what you may notice here, as I kind of go back to the previous example, is that we have this factor right here, this x squared. Because I had 2 copies of x, we would say that we have a multiplicity of this 0 of 2, because there were 2 copies of that x where that 0 came from, okay? These other factors, they only have 1 copy, which we might go ahead and signify there by writing the exponent there, and so we would go ahead and say that we have a multiplicity of 1 for both of these other zeros. So you're just looking at the exponent of the factor where these zeros came from, okay? Now, depending on the multiplicity, that's going to tell you if you're going to cross the x-axis at that location, or if you're going to bounce off of the x-axis at that location, okay? So if your multiplicity is even, then that is going to be a place where you're going to bounce off the x-axis. And if your multiplicity is odd, then that's going to be a place where, of course, you're going to cross the x-axis at these locations, okay? And, of course, that information is summarized here on this next slide where it says the multiplicity, of course, there is this number k that we're pointing out. And then, of course, here, if k is odd or if it's even, you're going to either touch or cross or bounce on the x-axis. So if we take a look at an example of that, f of x is equal to this function formula here, already factored for you, you'll notice that the multiplicities are stated in the exponent of these factors, okay? And keep in mind the factor x minus 6, that has one copy of it, so we would go ahead and state that the multiplicity is 1 on that 0 of 6, the multiplicity is 2 on that 0 of negative 3, and the multiplicity is 3 on that 0 of 0 itself, right? And so what that's going to mean, of course, is that we, of course, are going to be crossing at this 0 and at this one because the multiplicities are both odd. But we are going to be bouncing at that 0 of negative 3 because the multiplicity turned out to be even there, okay? And we can go ahead and see that here in the graph over here, right? We have the negative 3 where we, of course, bounced off of the x-axis. We have this 0 at the origin where we went ahead and crossed right on through. And then we have this other 0 of positive 6 where you can see that we go ahead and cross through there as well, okay? What I also want you to notice is the shape of how we crossed through here, right? Because of the multiplicity of negative 3 being 2, we definitely see that the shape that we crossed in at kind of looks like a little mini parabola there, right? So a quadratic because the multiplicity turned out to be 2. The way that we crossed at 0 is looking more like a little bit of a cubic shape where we kind of slope down into the origin and then slope away from the origin there. It's not just a straight line straight through the origin there, so that's more of a cubic. That makes sense. The multiplicity would be 3 there. And then, of course, if you look at the 0 of 6, we just crossed through in what seems to be a straight line fashion, right? And that makes sense, too, because the exponent there happened to be a 1. The multiplicity happened to be a 1, right? So you can get a lot of information about what the graph is going to look like at each of these x-intercepts by simply looking at the multiplicity of each of those zeros, okay? So let's go ahead and put a lot of this together here. We're going to look at the same exact graph that we looked at in the previous example, which I've already gone ahead and factored and found the zeros for you. We've already talked about the multiplicities there as well, so I'm just kind of stating that again, that we would cross or bounce at these respective places. And then what you'll also see me doing here is going ahead and trying to find some other points to plot, right? So I know that I can graph my x-intercepts, but I'm also going to give myself some other points to plot, and I've just demonstrated the work for one of them here, just plugging in an input of 1, getting an output of 4, just to go ahead and signify that you could do this with as many points as you like, and these, of course, give you some nice points to graph. So let's go ahead and talk through how we would go ahead and figure out the complete shape of this graph here real quick. I would go ahead and start off by plotting my x-intercepts here. So that's going to be at 0, 0, and at negative 2, 0, and at positive 2, 0. So at those locations there. And then, of course, you can go ahead and evaluate as many of these points as you like. I'm just going to go ahead and do 1, 4. And what we would now go ahead and do is just basically follow the steps that it says up here. So it says to determine the end behavior by using the leading coefficient test. So that's something that we did earlier in the video, right? So the leading coefficient here is going to be negative, and it looks like the degree, of course, is going to be an even number 4. And so that's going to tell us here that we have end behavior that is going to be pointing in the same direction. And because the leading coefficient is negative, we are going to be both pointing down. So I'm going to go ahead and draw something over here on my picture to just help me remember that for later, just a couple of down arrows on either side of my grid there. Because later on, whenever we put all this information together, we're going to have to keep that in mind, okay? So plot the zeros, which we've already done, and then determine the multiplicity, which I've already done down here, right? So the multiplicity at 0, 0, of course, is 2, because the number of copies of x that 0 came from, of course, was 2 there, okay? And so that's going to mean that I bounce, and then I cross at the other 2. Well, here's where you might need to put your thinking cap on and put multiple pieces of information together, because if the end behavior is going to be 2 ends that both point down, then that means by the time that I get to this 0 of negative 2 right here, I'm going to be below the x-axis. And if I cross through there, then that's going to mean that I cross through in a fashion where I start below the x-axis and I end up above the x-axis, okay? If I bounce at 0, then that means I'm already above the x-axis up here, and I would come down here and swoop down to 0 and then bounce just right off and stay above the x-axis, okay? Maybe coming up here to touch this point up here. So we can go ahead and start to graph what some of this picture would look like. And then as we go ahead and continue here, I would go ahead and swoop down and cross through this other 0 here and cross in that way. So it's not the most beautiful picture of a polynomial functions graph that you've ever seen in your life, but you remember that you have these graphing calculators and that you can go ahead and punch those in to figure out what they would look like here. So it looks like my picture is a little bit off. What I maybe should have done is go ahead and plug in -1. I might have seen that that would be 4 here as well. So we can go ahead and maybe do a little bit more of an accurate picture by fixing that up here really quickly. But you'll notice that all the information that we previously spoke about was something that we found in the picture of the graph in the calculator. So going and demonstrating that here one more time again, just to save time in the video, I've already gone through the whole factorization here, finding the zeros and the multiplicities of each. I'm just going to go ahead and start by using the leading coefficient test to figure out what my end behavior looks like. Of course, I have a +1 as my leading coefficient, and my degree, of course, looks like is odd. So that means I'm going to be climbing with ends pointing in different directions. So I'm just going to signify that on my graph over here, right? So I should have an end here that goes down. I should have an end here that goes up. So just kind of signifying that as I go through the rest of the problem. I'm not going to go ahead and plot my x-intercepts here. So I'm going to have an x-intercept here at the origin, x is equal to 0, and then over here at x is equal to 3 as well. And keep in mind that because of the multiplicities, I am going to be either crossing or bouncing at these locations. So because I have end behavior that starts down here at the left going down, I know that I'm going to be crossing through this 0 in this way, where I start below the x-axis and I cross through up above the x-axis. And then because the multiplicity on your x is equal to 3 is a 2, that means that you're going to bounce, of course. You're already up above the x-axis here, so that's going to mean that you're going to start above the x-axis and then swoop down and bounce right off of that 0. And then, of course, we have that end behavior that goes up like that. So you can go ahead and plot some other points here if you wanted to. I didn't really have any prepared here. So here is the picture over here on the calculator of what this looks like. And, of course, we already have all the information that we might need here to go ahead and draw a nice quick sketch of this graph, or at least have a general idea of what the shape would be, and that is going to be a complete problem. And that's actually going to do it for the video here. So again, just kind of taking all these different clues about what the polynomial graph is going to look like and putting them all together, you can create nice quick sketches of these polynomial graphs, and that's going to be very handy whenever we go to later trying to figure out that input-output relationship between polynomials. The graph is always very helpful with that. So I hope this video has been of some help to you. As always, if you guys have any questions at all, please feel free to let me know. But that's all I have for this video. Thank you very much for your attention, and I will speak to you in the next one.